Hi everybody. I would like to continue our notes on electrostatics. We're going to talk about voltage and electrical energy today. This right here is a wonderful piece of pop culture. This character's name is Egg Shen from the 80s classic Big Trouble in Little China. Feel free to watch it at some point and then just judge me for my awful taste in movies. I haven't watched it in a while. It probably doesn't hold up, but man, it's got some great quotes. They're just stuck in my brain. I don't know why. The important part is Egg Shen is showing you an example of a parallel plate capacitor right now. So his hands represent parallel plates. And a capacitor, as we're going to figure out, either through your lab or notes, is a device that stores electrical energy using a difference in voltage or charge from one place to another. The quiz, I got to figure out how to do a drawing quiz, so we're not going to worry about that just yet. But let's start off with a question. Why is it a little old bird like Tweety Bird is perfectly safe on electrical wires, but a bird like Big Bird, well, you know what he is. And it's not just because he's, a terrifying 6'5" creature covered in feathers, although maybe his size has something to do with it. Why is little guy safe on the power lines, big guy not so much? We're going to talk about that in terms of, you guessed it, static electricity and electrical energy. Alright? If you think perhaps it has something to do with wingspan, you're most likely right. But let's see why. I want you to think of these wires as different charges, because they do have a different voltage. Maybe this one right here is going to be negative and this one's going to be positive. If we think about the electric field that surrounds a charge, like just a lonely point charge right here, it has an electrical field that travels away from the positive in straight lines. And as you get away from the charge, the voltage drops. It decreases over time. Alright? These voltage lines, I want you to think of them as contour lines on a map that Mrs. Cruz would have taught you about. The closer together the lines are, the steeper that surface in the contour map. In this case, the closer together the lines are, the greater the potential difference, the greater the change in voltage over a shorter period of time, the stronger the electrical field. Now, going back to the idea of this power line right here situation, maybe the line on the left, imagine this dot represents the line extending into the screen and out of the screen. So that we're looking like head on at the wires. So that's one voltage. And then over here, we have a different voltage. That's the positive. Again, extending into the screen and out of the screen. We're just kind of looking at it head on. They have different voltages. And we're talking about like a different charge. So the voltage changes as you go farther and farther away from the individual charge. And you can see there's an electrical field between them. Now, if there's nothing that can carry charge in that field, well, no big deal. The field's there, energy's trapped there, but you can't get it. But what happens if you put something that actually bridges the gap between those two? Like, I don't know, a giant bird. Well, weirdly enough, the same thing would happen to a bunch of little birds as would a giant bird. So let's check this out. Right here, we have a whole bunch of birds sitting on power lines. Alright, so many of the power lines are being pushed down, but they're tiny. Alright, if we've got a voltage here and a voltage here, there's nothing to carry a charge through the electric field between them.
Look how thick they are. Look at these lines. Starting to droop. They're starting to get farther out that second line over there.
Now what happens if, I don't know, say not a big bird, but a bunch of little birds take off at the exact same time and get their wings close to each other? Yeah, you guessed it.
They're running out of power!
Now I like to think that that puff of smoke is actually just ionized gas and not ionized bird, but let's not dwell on that too much. So there is energy in an electrical field trapped in the electrical field between these two places of different charge. Alright, and that's why, larger birds are kind of in danger if they stand on those power lines. Alright, now think back to this idea of a contour map, where these equal voltage lines, lines of equal potential is what we can call them. Alright, think of them, as a contour map. When they're really close together, you get a steep slope on, a physical surface like hills that maybe Mrs. Cruz was having you map out, or a valley. When we have them in electrical terms, we don't think of them as contour lines. We think of them as potential gradients. All Alright, so as the voltage changes with a distance, so S is distance in this case, so the greater the voltage change over a short distance, the larger the electric field is going to be. So the larger the potential gradient, the greater that voltage, the smaller that distance, the stronger the potential, the stronger the electrical field. So if the lines are really close together, the field's really strong. If lines are really far apart, the field is really weak. Now we can tap into that energy the same way we might tap into gravitational energy. Remember way back in the first semester when we talked about picking something up? When you were picking up something like a baseball, alright, it's on the floor, you lift it up, you're actually doing work against the force of gravity. Alright, when you hold it up in the air, we have potential energy. Now in this case, potential energy is a U. U gravity, that's potential energy. So you do work, you store energy in the form of gravity, mass times gravity times height. If you take a look right here, we have our skateboarder. If I pick up the skateboarder and I put a little bar graph here, you'll notice the potential energy increases as I raise the skateboarder higher. That is because I'm giving the skateboarder more gravitational potential energy. If I let go while the skateboarder's in a gravity field, gravity's going to do work pulling the skateboarder down. Alright? And this potential bar is going to drop. And kinetic goes up. And then, thermal energy, bust your knees or your ankles if you're not bending and, tucking and rolling when you hit the ground. But when you do work against gravity, you increase the potential energy stored. When gravity does work, it takes away that potential energy. Alright? The same thing can be said in electrical fields. Now this is kind of like that parallel plate capacitor idea that I was talking about with Egg Shen. We have set charge here, we have an opposite charge here, and there's parallel plates. These are parallel plates, so the electric field runs from the positive towards the negative in a straight line. Alright? If you were to do work against the electric field, that'd be like putting this positive charge way up here. We can keep track of that electrical energy in terms of the charge, the field strength, and how far you move it in the field. But let's get to that. I want you to note that whenever you see capital UE, that is electrical potential energy. It is not electrical potential. Electrical potential is voltage. Electrical potential energy is U, UE specifically, and it's carried or it's measured in joules. Sorry, I had the sounds on my phone. Alright, now joules, kinetic energy, potential energy, work, all those things are measured in joules. And work, like doing work against an electric field, work is always going to be equal to a force multiplied by a distance. Alright, S is distance again. Alright, so work is force times distance. Well, in terms of electrical energy, so if we're talking about a force coming from an electric field, we need to remember our relationship between electric field, force, and charge. That's, let's see here, it's going to be this equation right here. So the electric field strength is equal to a force divided by the charge put inside the field. So this charge right here would be feeling a force if it was put in the field. If we just do the algebra and cross multiply, we can get that a force is equal to the electric field where a charge is put. Well, now if we take this expression for force and plug it in right down here, we get an idea of how we can measure the work done inside an electrical field. And it's the same as this right here. Alright? So if you move this positive charge up, you're doing work against the electric field, which means you're storing electrical potential energy. That thing wants to drop, just like the skateboarder wanted to drop in a gravity field. So you store energy in a field by pushing something against it. And that's how we get our work. Alright, so just keeping things straight, we have electrical potential energy and work in terms of the work done when you increase or decrease electrical potential energy. So a positive charge moves in the direction of the electric field. That's how it should be. So the field goes down. So when this charge experiences a force pushing it down, and it moves down in the direction of the electric field from positive to negative like it should, the field is doing positive work on the charge, and the potential energy, the electrical potential energy of this charge, will decrease. Same thing over here. Alright? This negative charge, it wants to go up. It wants to go against the direction of the electric field because it's an opposite, and opposites attract. The negative is attracted to the positive. So if the charge moves up, the field does positive work, electrical potential energy decreases. But if we do something to make them move against that, say we have a positive charge that's all the way down here, and we push it up here, well, in that case, the field is doing negative work on the charge, and we increase the electrical potential energy. We basically store energy right here. It's like lifting up that skateboarder. Alright, so electrical potential energy increases when the field does negative work, when we move something against the field. Same thing over here. There's a force pushing the charge from here to here. If we move the charge down from position A to position B, then we have done work. The field did negative work. We stored electrical potential energy in this charge. Alright? Okay, so I just want to finish this off by giving you a little bit of context for how this was used at some point in physics. Alright? So, a guy named Robert Millikan, did an experiment that actually allowed us to determine a lot of things about electrical energy and also electric charge. It's one of the other ways we established what the individual charge of an electron or a proton would be. So he had this atomizer, something that would spray out a very fine mist of oil and at the same time charge the oil up. The oil mist would fall down and droplets would fall through a hole right here in the top of this plate capacitor. So it's basically like a disc. The top disc is all positive, the bottom disc is all negative. Droplets of oil would fall through, some would stick on here, others would just fall right through. And he would increase the voltage between these two plates. By changing the charge on the plates, he'd increase the voltage until the oil drops would hover. He would actually be able to look at it through a little lens and see the oil drop hovering in place. By doing this, he was able to figure out, alright, the electrical force holding it up must be equal to the weight of the individual droplet. You just got to figure out the density of the oil and the size of the droplet, and you get all that idea for the force of gravity on it. Apply the voltage, you get that exact force going up. That tells you something about the strength of the electric field. And carrying it through, he was able to determine, here, I'll skip this real quick, he was able to determine the individual charge of an electron. So he suspended oil drops of various masses between the parallel plates of a capacitor. His determination found many different multiples of the same number. Remember we said before charge can't be quantized? So you can't find like 1.5 protons. You can only find the charge of 2 protons or 1 proton. He found that the charge of these charged up droplets of oil were always multiples of this number. And that's where we got our measurement for the elementary charged particle. 1.6 times 10 to the minus 19 coulombs. Positive for a proton, negative for an electron. Alright, now we're talking about the electrical energy used to make something move or move against a field like this. It's a small number. We call it an electron volt. So when an electron moves through a potential difference of 1 volt, its change of potential energy is 1 electron volt. So from this equation, electrical energy is equal to voltage times charge. So 1 volt, 1 individual charge, we get 1 electron volt, 1.6 times 10 to the minus 19 joules. So if I ask you something about the energy of a charge, I'm probably going to ask for it in terms of electron volts right here. But just understand that that equates to a very small amount of joules, and that is more than enough, almost 15 minutes of talking right here. Please take notes on this and understand that I'm going to give you a sample problem using a little bit of this information and assign you some homework. Please feel free to contact me anyway. I've heard back that Google Meet is probably the best way to do it. If we were to actually talk, I am more than happy to do that because I am really missing just hearing the really good questions you have, even if they're really totally off topic. I miss seeing you as a class, so I'll set something up once I figure it out, and once maybe somebody walks me through it. Have a great day. Comment with any questions, and I'll be seeing you.